I kind of intimated there at the end of the last video that that portion from the previous problem, which was part C, is a very important thing to look at. It's called the harmonic series. So you know if it has its own name, then it's got to be important, right? And it is. So the harmonic series is something that's going to come back again and again. So it's a very important and very mathematically intriguing series. So the limit, of course, of this is 0. The one, a half, a third, a fourth, a fifth, right? So you'll notice those individual terms are going to 0. But what about the partial sums? So if I take s sub 1, that would be 1. S sub 2 would be 1 plus a half, right? Which is 1, which is 3 halves, or 1.5. Then if I take s sub 3, that would be 1 plus a half plus a third, which is 11/6. You can check it on Desmos if you don't believe me, but it is, which is 1.83 repeating. S sub 4, first 4 terms, would be 1 plus a half plus a third plus a fourth, which would be 25 over 12, because 12 is the least common denominator there, which is 2.083 repeating. So that's what partial sums are. So it's a sequence. There's the first one, there's the second one, there's the third one, there's the fourth one. So we're making a sequence of the partial sums. So now we want a general formula for that partial sum. Well, that would of course be, we don't have to get too fancy about it. It would just be, we want to start at 1, we want to end at n of 1 over k. All right, so then what if we graphed this? So, and I don't think this is super useful. I got this from the book, but let me show you that graph in Desmos real quick. And I'll post this for you all. Oh, give me 1 second. Here we have it. So I have the function f of x is 1 over x. And you can see the sequence for the orange dots. The orange dots are what we proved in the previous example, that these values are going to 0. And you can see it. Those dots are getting smaller and smaller and smaller in terms of their y values. So as the x increases, right, as we go to infinity, it's getting smaller and smaller, closer and closer to 0. However, if we add those sequence values, so this dot and this dot together make that black dot, and these first 3 dots make that black dot, and so on. When we add those together, what we see is this sequence right here. And that's the graph you're looking at when you look at the page right here. That's the graph right here. And of course this goes out to 180, but you can see it's steadily increasing, right? It's not going to 0. It's not converging to anything. It's getting larger and larger and larger. And I can prove that over in the table, even though I don't have to see the dots. You can see down here, it's not stopping, right? It's not getting closer and closer to a value. So at 10,000, I'm at 9. So if I do 10, or 100,000, excuse me, it's at 12. And if I do a million, it's at 14. It's not converging to anything. It's just going to infinity very slowly, but nevertheless going to infinity. I'll save that graph for you all, and I'll post it. All right, so we can see this is the sum. This isn't the sequence, because the sequence itself goes to 0, right? But the sum, right, the partial sums are diverging. Right? They're not approaching any particular value. Converging, by the way, does not have to mean converging to 0. Remember the geometric series. You can converge to 3. You can converge to all sorts of things. All right, so let's looking at that in a different way. If you look at the Riemann sum, then what's happening? Well, if I add up 1 plus a half plus a third, right? So that's the left Riemann sum, right? So if I think about the area of this rectangle, that's 1, right? So S sub n equals 1 plus a half plus 1 over 3 plus 1 over 4 plus 1 over n. That is the equivalent of the left Riemann sum. See how we touch on the left here? So this is the left Riemann sum. All right. Now, because 1 over x is decreasing and the Riemann sum is an overestimate, let me just write that down. Because, I shouldn't say this isn't equal. And because the left Riemann is an overestimate, so because y equals 1 over x is decreasing constantly, the left Riemann sum, i.e. the partial sums, is an overestimate. Right? You can see it in the graph. The rectangles are larger than the graph itself. Okay, so that means that those Riemann sums, that partial sum, is larger than the integral from 1. Okay, so Riemann sums, they start here and they go over. So if I want that nth partial sum, that would be adding up this rectangle right here. And that rectangle is right there, and it ends at n plus 1. So at n, my integral, not at n, but at n plus 1. I'm basically just proving that this works, of that function, 1 over x dx. So the region, right, from 1 to n plus 1 is smaller than the partial sums, the Riemann sum. Okay, well, I know how to integrate that, right? That means that S sub n is larger than the integral of 1 over x is the natural log of the absolute value of x. I'm going to take it from 1 to n plus 1. And that would be the natural log of n plus 1. I don't need to worry about the absolute values because n plus 1 is obviously positive. Minus the natural log of 1. But the natural log of 1 is 0, so that doesn't do anything for us. So this means that as n goes to infinity, this goes to infinity, right? But we know as n goes to infinity, the natural log of n plus 1 goes to infinity. Therefore, the partial sums, because we're saying S sub n is greater than this, and this is infinity, therefore S sub n is infinity also. In other words, we just proved, using an integral and some fancy thinking with Riemann sums, we just proved that the harmonic series, well, I guess we proved this theorem down below. The harmonic series diverges. Okay? So if you're thinking, oh, I'll need to, be able to do this Riemann sum thing all the time. No. This was just a little tricky proof thing. But it's good to think about. So it's kind of helping you ponder, how these things work and what are some other ways we can prove things. And we will go back to integrals again later in this section. So we will do a little bit with integrals. But just think about what we're doing. The harmonic series, 1 plus a half plus a third plus a fourth, can be represented by this Riemann sum. Right? But this is the left Riemann sum, which you can see is an overestimate. It has all these overages on that curve. So therefore, that sum is greater than that integral, because the integral is the area underneath the curve, and that sum is obviously larger than that. But I know what that integral is, and that integral goes to infinity. Right? This area is infinitely large as n goes to infinity, and therefore so is the sum, because the sum is bigger than that, because of all those little bits of box over the curve. And that proves that the harmonic series diverges. And now we know that forevermore. We will never need to prove it again. The harmonic series is a very intriguing series, and it has even more implications than this, but this is where we're going to start. It diverges. Even though its sequence values, 1, a half, a third, a fourth, a fifth, are shrinking. And you can see that in the Desmos graph. So the sequence itself, which is the orange dots, is shrinking, right? They're going to 0. Look how tiny they're getting. But the series, when you add those dots up, is diverging. Right? It is a divergent series. Sorry, I've got to get my camera back. Now, what does that mean for these other ones? Well, this is 5 times 1 over n. So this is 5 times the series from n equals 1 to infinity. Okay, so since this part diverges and goes to infinity, here, this diverges. Guess what 5 times infinity is? Infinity. Therefore, it's all good, right? And so this series diverges. It doesn't matter if you multiply by a constant. Right? Multiplying by a constant, it's still divergent. I guess that's what I'm going to say here. Does not matter. If you multiply by a constant, it will still be divergent. Okay, what if I start somewhere else? What if instead of multiplying by a constant, which is what I was doing here, 5, what if I start at 4? It's not going to matter. Right? It's still going to be divergent because this is the same as the series from 1 to infinity minus the partial sum from 1 to 3. Remember the partial sums? Okay, so this is infinity, and we're going to take away, well, 1 plus a half plus a third, which I think was 11/6 on the previous page. So you have infinity, and you take away 11/6 of that. You know what you still have? You still have infinity. Therefore, it diverges. Right? So we've proven that the following series are divergent. So it doesn't matter if you multiply by a constant, it's still going to be divergent. The harmonic series is so fascinating. And it does not matter where you start. Actually, I should make that arrow go right to that 4. It does not matter where the series starts. So as long as you have a harmonic series, it will be divergent. It doesn't matter whether you multiply it by a constant. Even if that constant was a fraction, it wouldn't matter. It would still be divergent. And it doesn't matter where you start. It doesn't matter what your starting point is for your series. It will still be divergent. If it's harmonic, it diverges. Period. And the harmonic series is a very important series.